Hey guys, so in this video we're going to go over what unstable and stable nuclei are. Before we started, I want to make sure we're okay with actually what's inside a nucleus or what's part of an atom. This is something you did at GCSE. If you did your chemistry in GCSE, it's also part of your GCSE physics. But just to review it, hopefully we remember that the bottom number is always equal to the number of protons. So if I want to figure out the number of protons in my chlorine 35, I know there's 17 protons. If I want to figure out the number of neutrons inside my chlorine 35, what we do is you do the top number, take away your bottom number. So I do 35, take away 17, and my mental math is shocking, but I'm pretty sure it's 18. So 35, take away 17. Yeah, we're going to get 18 neutrons. And then to get our number of electrons, we know that it's electrically neutral. So what that means is we have equal numbers of positive charge and negative charge. So I've got 17 positive protons, I need to have 17 negative electrons to balance it. Hopefully you're thinking, here also is chlorine, okay? It's the same element, both are chlorine, but they're different atoms. So hopefully you're thinking, what these are here, these are my isotopes. So remember, isotopes you're going to see quite a lot in physics. Remember, isotopes, what they are they're different atoms of the same element, both are chlorine, with the same number of protons, because this one also has 17 protons, but they have different numbers of neutrons. So if I do here, 37 take away 17, I get 20 neutrons. So I can see this chlorine 35 had 18 neutrons, but this chlorine 37 had 20 neutrons. If I look at my number of electrons then, because it's an atom, it's electrically neutral, I have equal number of positive protons and negative electrons. So 17 negative electrons. The next thing then you want to look at is something called the specific charges. So specific charge is not on your data sheet, it's something you have to know. Specific charge is always the second word, so it's just charge. And what you do is you divide it by the mass number, okay? This is the next part then that comes in for physics. You're told in your GCSEs the charge of a proton is +1, but that's its relative charge. It actually doesn't have a charge of +1, it's got a relative charge of +1. An electron is a relative charge of -1. Because what its real charge is 1.6 times 10 to the negative 19, that's on your data sheet, and the real charge of an electron is negative 1.6 times 10 to the negative 19. So you can see why they got the number 1. They just divide it through by this number. So 1.6 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19 gives me 1, positive 1. Okay, so again, they're called relative charges. So if I want to find what the specific charge is of my chlorine 35, let's say we want to look at the specific charge of the chlorine 35 nucleus. Okay, if I want to look at just the nucleus, I know the only things in there are my protons and my neutrons, okay? I know neutrons have 0 charge, so the only thing that's going to have charge there are my protons. So to find out the specific charges of the chlorine 35 nucleus, I'm going to take my charge of my protons. So I told I got 17 protons. Remember, it's a relative charge of 17, so actually 17 multiplied by 1.6 times 10 to the negative 19. And we're going to divide by its mass. Okay, so again, in GCSEs, you were told the mass of a proton is 1, the mass of a neutron is 1, but mass is not actually 1, it's a relative mass. Okay, so if you look on your data sheet or your equation sheet, you can see what the mass of a proton actually is and what the mass of a neutron actually is. So again, I got 17 protons, so 17 times my mass of my proton on my data sheet is 1.673 times 10 to the negative 27 kilograms, which makes sense, it's a really small number. And we're going to have to add that to the number of our mass of our neutrons, which is 18 times 1.675 times 10 to the minus 27. So when we do this math, we can figure out what the specific charge is of our chlorine 35 nucleus. Okay, so key learning here is that charge of electron is not actually -1, it's negative 1.6 times the negative 19. The mass of proton is not actually 1, it's the mass that's on your data sheet in kilograms. Okay? So now we know what's inside our nucleus and our atom. We're thinking about what is an unstable nucleus. Okay, so an unstable nucleus, you might think about something like uranium-235. So uranium is a really, really large nucleus, right? We see its mass number is much bigger than chlorine. Because it's really large, we say that it is unstable. And if something is unstable, it wants to become stable by releasing some type of energy or some type of particle. Okay, we call that radioactive decay. Okay, so the nucleus can emit 3 different things that you've probably learned about in your GCSEs. We know alpha particle decay, we have beta decay, and you've got gamma decay. Okay? In GCSEs, you learned what alpha, beta, and gamma particle were, and hopefully everyone learned that an alpha particle is a helium nucleus. Make sure you say the nucleus because we're only looking at the nucleus. So it's 4-2. There's no electrons there. So if we're only looking at the nucleus and there's 2 protons, it's got a relative charge of +2. Beta decay. There's 2 types of beta decay. There's beta minus, 0, -1, and there's beta positive, 0, +1. So 2 different types of beta decay. And you would have learned in your GCSEs that beta decay is a fast-moving electron emitted from the nucleus, okay? So a fast-moving electron is going to be this one. It's a negative charge. Electrons are negatively charged. And this one is going to be your first introduction to antimatter. We're going to do a video later on what antimatter is. But this one is actually called a positron. So it's just the same thing as electron, same mass of electron, it's just got the opposite charge. Gamma, you learned, is an EM wave. Okay? So there are different types of radioactive decay that can occur in order to make this uranium nucleus more stable. Okay? And how do we know which one's going to occur? So what we do is we look at this graph here. It's called an NZ graph. N tells us how many neutrons there are, and Z represents the number of protons, and that's just something you need to know. Okay, so Z is your protons, N is your neutrons. You can see my dotted line here is when there's equal numbers of protons and neutrons. So the first 20 elements, so up to a mass number of 20, there's always equal numbers of protons and neutrons. So there's 20 protons, so there'll be 20 neutrons inside that nucleus. But when we get to heavier atoms, what happens is the stability line starts to curve upwards. So what does that mean? Let's say we looked at an element that's got a mass number of 90. If I looked up at 90 protons, the dotted line would tell me there's going to be 90 neutrons, but it's not there. It's at the solid line. So there's not 90 neutrons in it. There's much more. Maybe there's something like 150 neutrons. So we can see here the line bends, that more the stability line, stable nuclei, want to have more neutrons in their nucleus than protons. You think, why would a nucleus want more neutrons than protons? And you should have thought about this earlier, but you probably never did. We just said inside that nucleus, we always have neutrons and protons, right? Neutrons and protons, neutrons and protons. What you should have thought about is, how does that even exist, right? Because you've learned that protons, if they've all got a relative charge of positive, if protons are all positive, surely we know they're going to repel each other, electrostatic force of repulsion. So they want to repel each other. So sure, that nucleus is split apart. But that's when we know we've got another force inside the nucleus, and that other force inside the nucleus is called the strong nuclear force, and it acts between the nucleons to pull that nucleus together. So the strong nuclear force. So again, what happens is, why we want to have more neutrons than protons is because the protons want to repel each other and break that nucleus apart. But if we put more neutrons in there, we can get more of that strong nuclear force to hold that nucleus together. And there's a graph that you need to know for this. So the graph is, on this axis, we're going to put femtometers. So a femtometer is 1 × 10⁻15 meters. That's roughly the size of a nucleus. Okay, up here, we're going to say that this is repulsion. And down here, this is my attraction. And you always have to mark on the numbers 0.5 and 3 femtometers. Because the strong nuclear force, less than 0.5 femtometers, is repulsive. Between 0.5 and 3 femtometers is attractive, and then it goes off to 0 because it's really short range force. It only acts within the nucleus. Whereas the electrostatic force of repulsion, that force is infinite in range, so it's always going to act, and it's always repulsive because the protons want to repel each other. So that one is going to be infinite in range and always repulsive. Okay, so we see we've got both those forces acting inside the nucleus. To see which type of decay occurs, we have to see where does the element fall. So let's say the element falls here on this side of the stability line. Clearly what that tells us is we have too many neutrons. We're on the side of too many neutrons. So if we've got too many neutrons inside the nucleus, there has to be some way to get rid of that neutron, okay? So if there's too many neutrons, I want to get rid of that neutron. The only way to get rid of the neutron is going to decay into a proton, okay? And what we do here is we look at our charges. So a neutron has 0 charge, a proton has a relative charge of +1. So to balance the charges, I need something over here to cancel out that positive charge. So that's going to be my electron. So you can see here, if there's too many neutrons, we're going to emit a fast-moving electron from the nucleus, and that is our beta minus decay. So if there's too many neutrons, we're going to get beta minus decay. The other thing that gets emitted here from the nucleus is called a neutrino, an antineutrino. And we're going to look at a later video how you figure out that that's an antineutrino. But right now, we're just concentrating on how do we know that it was a beta minus decay. Okay, if our atom falls on this side of the stability line, clearly the problem is here we have too many protons. So if I've got too many protons, I think what's going to happen to my protons? If there's too many protons, I want to get rid of a proton. So what's going to happen is my proton has to change into something. So in this one, my proton can only decay into my neutron. And again, I want to look at my charges. So I got a +1 charge here, a 0 charge here. I need to balance it. So I need something with a +1 charge here. So that's why it's going to be my positron or my beta positive decay. My beta positive decay. And the other thing that gets emitted from the nucleus is going to be a neutrino. But again, we're going to learn about how you figure this out in later videos. So again, what we're saying, if there's too many protons, we know that what's going to happen there is our beta positive decay. Okay. So if we look now at my question, what we're trying to do here is figure out what is going to get formed for each three of the decays. So for the first one, we got alpha decay. So alpha decay, I know is my helium nucleus. A helium nucleus, we just have to remember the numbers, 4, 2. So anything that undergoes alpha decay, it just means it's too big to begin with. It's not that there's too many neutrons or too many protons, there's too many of everything. So alpha decay happens when there's really large nucleus, when there's too many of everything. So it emits an alpha particle. We know the top number is going to drop by 4. So that's why this one's going to end up being 360, 300. My mental math is shocking. 236. The bottom number has decreased by 2. That's going to be 92. So you can see what those numbers are going to be. If, again, we're doing beta minus decays, remember beta minus decay is because in here we have too many neutrons. In beta minus decay, there's too many neutrons. One of the neutrons is changed into a proton. And we can see that here because beta minus, we know from our GCSEs, we represent 0, minus 1. So if I've got 14 here and 0 here, that's going to be 14 to balance it. 6 here and a -1 here, that has to be 7 because 7 take away 1 gives me 6 to balance here. And hopefully what you can see here is that the proton number went up by 1. We increased the number of protons. And that makes sense because that's exactly what we said happens in our beta minus decay. We made a proton because our neutron decayed into a proton. So we increased the number of protons. And again, just because we have to balance the equation off, which we're going to learn how to do in a later video, we know the other thing gets formed there is going to be my antineutrino. Okay, in the last stage, we've got beta positive decay. So this one, beta positive decay, tells us there's too many protons inside this nucleus. So if we balance our charges, 22, 0, this has to be 22. 11 plus 1, this has to be 10. And we can see what happened there is one of my protons got lost. Because in beta positive decay, when my protons decayed into a neutron. And then the other thing that commits here is my electron neutrino. And again, like I said, you're going to learn how to figure out what's the other thing emitted later. But the main thing right now, you just have to learn that neutrinos always have 0 charge. That's why we keep it balanced. They always have 0 charge. And the quick way to do it, it's not the best way to do it, the quick way to do it is to see if I have one real particle here, I have made 2 real particles, so I need an antiparticle here to cancel it. So the line on top of it tells us an antiparticle. Remember earlier we said electrons are real particles and positrons are our antiparticles. Here I've got 1 real particle, I've got 1 real particle here, but I've got an antiparticle. Because remember a positron's an antiparticle, so we need another particle, real particle to balance out. But again, the best way to do it is to look at lepton and barrier number, which we're going to learn to do in a later video.